Hello everyone, welcome back to today's last session of the day. It's my honor to introduce our speaker of the day, Mr. Abhay Phansikar. Sir is an industry expert having 35 plus years of solid IT experience and has played various roles including director, president, COO and technology architect. Currently, he is a business development director at Agilent Technology Private Limited. He is a senior member IEEE and immediate past chairman of IEEE Bombay section, and also the mentor of Startup Bootcamp, one of the top 3 global accelerator for the startups. Some of the systems developed by Sir including mission critical military grade system, air traffic control simulators, radar tracking system, healthcare ERP and portals. I'm, I'm welcome you, sir, on the behalf of Shine Kachi Engineering College. I am sure this session will be very useful for all of us. Now I'm requesting our speaker, please take over and start the session. Over to you, sir. Sir, please unmute yourself.
Thank you. Thanks for the introduction. I'll just open my presentation. PowerPoint. Yeah, so good afternoon, everyone. Today I'm going to talk about LoRaWan. LoRaWan typically is a new technology which is developed specifically for IoT applications. And my intent today is to run you through the fundamentals behind why this technology got developed, why it is becoming popular, and talk about some of the features of the technology, both from an basics perspective and an applications perspective, and share some examples of where it is being used. Is it okay if I stop sharing my video so that you will get a better bandwidth? Okay, let me see. If there's a problem, then I'll stop sharing my video. So this is an old slide which was picked up from Cisco Internet Business Solutions.
Sorry to interrupt you, sir. Sir, please minimize that window.
Yeah.
Small. Thank you, sir.
Yeah. Is it better now?
Yes, sir.
Yeah. So 25 billion connected objects by 2020, and it is kind of becoming a reality, mainly due to COVID situation. Now people are using more and more connected objects, connected devices, and because of virtual working, they are now being forced to use some of this over the internet. And Internet of Things is gaining a whole lot of popularity. It is being used everywhere. I'm not sure how clear this slide will be seen on your screen, but if I go from left to right, in the left you will see that it is used for understanding the bridge and its structural characteristics. It is being looked for forest fire detections, the quality of food. If you go into city, manufacturing, pollution levels, parking assist, then perimeter tracking, traffic management, smartphone detections, and smart cities, which include smart lighting, smart roads, as well as new things that are coming up are intelligent shopping, vending machines in a different configuration, and on top of that, everything that's really becoming more popular is meter reading and waste management, those kind of solutions. So I'll go fundamentally as to why a need for new technology has come in. It is to do with power and communication bandwidth consideration. So if you look at 25 billion connected devices, so I mean, just take an example. We have like 8 billion people on the planet, and 4 billion people are connected with cell phones. So if you look at my first row, which says 4000 milliamp hour and 5 volts. If I look at simply just the cell phones and assuming that cell phone is charged only once, so we have 4 billion devices that are being used in a day. And if you look at the power taken by them, it's like about 1/6 of this, so 24 gigawatts. And maybe if everyone is not using it at its full potential and full level, maybe still 20 gigawatt, 30 gigawatt power is just being used to power the cell phones. And if you look at something like a 150 milliamp current requirement and a 3-volt battery for 30 days, you'll see that it requires 1 gigawatt. So from 25 gigawatts per day, which is like 1/5 of India's power, and maybe 10 times the power what Mumbai uses. From there, if we use 25 billion devices, but if we simply make them low power devices, we are looking at 1 gigawatt of power in a month. So that's the huge difference if we are able to save power with the IoT devices. And the same thing goes with communication bandwidth. If suppose they are using 100 megabits per day, we are talking of 2500 petabits of communication bandwidth requirement. And if they go to 1 kilobyte per day, we are just looking at 25 terabytes of communication bandwidth. And that is a huge, huge difference. And as we know that today's IoT devices, many of them are working on technologies that are not really power and bandwidth aware. Like IoT devices are being connected using Wi-Fi and home network, which itself is a high bandwidth network. So if you look at the need for new technologies, and especially when smart city concepts are taking off, where you have automated meter reading that's likely to happen even in India in many places, and outdoor street management, traffic management, those kind of things. If we were to use traditional cellular technologies, these technologies are designed for broadband communication. So fundamentals of telecom GSM technologies that are currently popular or going to 5G, they are basically broadband technologies. They are always on, always aware. And even if you see currently, if your cell phone, if you're not even going to use a single data bit for a day, or your laptop, if you look at the bandwidth usage that the phone has taken just to remain connected with the telecom operator, you will be surprised. I mean, these devices are really, really power hungry and bandwidth hungry. And they are unsuited to low cost, low data rate devices and applications. So typically, if you look at a water meter reading or an electricity meter reading, it's going to send very few bytes of data in a day. Or even if you are going to look at slightly continuous amount of monitoring of these machines, but a meter reading simply needs to send its power reading, and that's all, few bytes of data. And to send those few bytes of data, if you use a communication technology which consumes heavy bandwidth, I mean, if that meter is connected to your Wi-Fi network or a GSM network, it becomes very, very expensive and costly. I mean, the meter would need some kind of a GSM chip inserted into it, or it will need to be configured to connect with Wi-Fi. And existing wireless technologies such as Wi-Fi or Zigbee. If we consider home Wi-Fi, which is low power, or Zigbee, or even Bluetooth, we are talking of coverage of 10 meters, 20 meters, or in a kind of clear signal scenario, you may be able to communicate say 50 to 100 meters. So if we were to use these kind of technologies that are currently existing, will require too many gateways to ensure a good coverage, and also too much of management headache to ensure this with device management, traffic management, handing over and all those things. So to eliminate this, people have come up with a new technology which is low power, wide area. So LoRaWan basically says it's long range, low power, wide area network. And LPWAN, Sigfox, Link Labs, they are the people who have kind of come out with these devices, fundamentally using the same principles that are being used, and collectively they are LoRaWAN technology. So basically, we now have one platform which is serving all the applications. It's low power wide area network, where the gateways can connect to devices which are 3 to 5 kilometers away. A significant scale over the current Wi-Fi, home Wi-Fi or Zigbee technologies. Here, we just put one tower, and we have seen, I mean, our experience is even in city, we get 3 to 5 kilometers very, very easily. In open areas, we are getting close to 15 kilometers. We have seen that. And these devices are consuming extremely low power. That is, the battery life is as high as 10 years. What's the downside of this? The communication systems are optimized for low data rate connected objects, which are mainly sensors and actuators. So if you were to have a temperature monitoring system, so one of the popular applications of IoT which is used by agriculture is they look at the moisture content in the field. So they are monitoring the moisture and then they start the sprinklers. Now here what we just get is an on-off situation, a sprinkler based moisture sensor reading. So it basically, all the sprinklers have their moisture sensor attached to them, and they send that data, very low data. Or if you are looking at temperature, ambient temperature, or if you are looking at the pollution, either it may be sound pollution or it may be air pollution. All of these devices are simple sensor devices which are sending data back into the system. So this communication system is optimized for low data rate objects, which means we are just working in a bandwidth of say few bytes to 10 kilobytes. One more consideration of these devices to make it low power is to eliminate the electronics as much as possible. So a typical LoRaWAN chip is just for connectivity to the tower, and a LoRaWAN solution rarely includes a GPS. See, you need to know the location, and the way to know the location is either by pre-marking it, which means if the device moves somewhere else, if the sensor moves somewhere else, you will feel that the data is coming from an old location which is not correct, or else you put a GPS. So along with the data sent by the sensor, you also send the GPS location, which will help you identify from where the data is coming. LoRaWAN allows you to eliminate the GPS also. So if you have more than 2 gateways within a particular area, a LoRaWAN device will connect to all the gateways. That's the fundamental of LoRaWAN. it connects to all the gateways within the area, and based on how they connect with the gateways, you will be able to understand the location of the device. If you do a simple straight line from the gateways and the device, they will intersect at the point which is the gateway point. So it's called as triangulation. So triangulation will provide you location services, and this way you get a substantial advantage over cost, size, power, or traditional systems of connected objects. So here's an example of a wireless sensor network that we had been working on. It shows a photograph of a gateway which has been installed in Zurich and its coverage. So we are getting a coverage of almost 4.5 kilometers in Zurich. And here you could put it by just one gateway if you're not worried about triangulation, or you could put more than one gateway within the same area, and these devices will connect to that gateway, and you will also know triangulation. Now, this is a typical outdoor gateway on the right side, which I have shown. It's small in size, and it's able to cover the whole area. And we have shown the typical device. If you look at the device is very small. I mean, the lower figure on the right hand side indicates that the device is almost of the size of 1/4 size of a pencil, which is basically just a small battery cell size of a device. Now this is the pollution monitoring device, which is kept spread across all over the city. Now what we are saying is this device will last us about 10 years. So the advantage of LoRaWan is effectively seen over here. You can simply put this device in various buildings, in various balconies of buildings, or other locations where you want to monitor pollution. And there is no installation cost, there is no configuration cost. If you ask someone to put it in their house, they are not worried about any great amount of interference, or that they have to give a power connectivity. All of that is kind of taken care of. The technology that is used behind this is RF, the fundamental technology. So even if this device is kept inside a room, it will be able to communicate. Only thing is, in that case, it will pick up the air pollution quality within that room or this particular device as it is shown. I mean, it could have a temperature sensor inside it. It could have a sound pollution, a sound monitoring sensor inside it, or it could have just air quality monitoring sensor, gas monitoring sensor inside it. All of this can be fitted in such a small area. So as you see, much lower devices battery size and cost than a similar cellular device. If we were to connect using, say, either any NB-IoT kind of thing or cellular technologies, it would require a higher device size. It would require a charging circuit because the battery would not last for that long. It also says much lower network deployment cost than shorter range networks. So shorter range networks require you to do some amount of configuration. Here maybe you do once the configuration and then forget it. You don't have to worry about power, you don't have to worry about charging, you don't have to worry about restarting and those things. So I have laid the fundamental of how LoRa can be advantageous to IoT, and then we'll go down to what this technology is. So LoRa is a disruptive wireless long-range technology, and it basically came up to have a huge amount of performance improvements in automated meter reading and machine-to-machine and IoT kind of communication. It gives you a range improvement which is very dramatic, 10 to 50 times range improvement over standard devices, and power which is significantly lower. So I'll kind of go into more details of what this technology is. So LoRa uses spread spectrum modulation scheme. Spread spectrum modulation scheme is typically you modulate a signal over multiple frequencies, hoping that some of the frequency would get caught by the listening device and they will be able to receive that signal, which is against the principles of narrowband technologies, where you keep the band very narrow and pack far more information. The second thing is, it is an extremely efficient modem architecture and it increases the range by 10x. If you look at the sensitivity versus data rate figure over here, when we are talking of say 1 Mbps kind of data rate on the right hand corner at the bottom, you're looking at a power of say minus 90 dBm. Whereas LoRa, what we are looking at is a power of minus 140 dBm. And to work in below minus 125 dBm, what we are trading is data rate. So we are working at less than 1 kbps to 10 kbps kind of data rate. If you look at the signal power that's taken by various devices, so 1 dBm basically means 1 milliwatt of power, and the scale is logarithmic. 10 dBm means 100 watt of power. So if you look at certain devices that are taking power, you have 32 milliwatts of power taken by the wireless transmission in your laptop. You have minus 100 dBm of a very good Wi-Fi network. We don't really have that kind of a network. We generally have a minus 10 dBm, that's 100 microwatts of power, which is basically taken by our signal networks. And if you look at a GPS is working at minus 111 dBm to minus 127.5 dBm. So when we are talking of LoRa, and when we are talking of a range where we are saying that it will work in minus 120 to minus 140 dBm kind of a power range, which means I'll go to the next scan. This is a spectral scan which we have taken at Shah and Anchar College of Engineering, Chembur, that's our college. And here if you see, there's a lot of noise that's happening between minus 60 to minus 120 dBm. This is where there's a lot of chatter. We have our RFID transmissions, Bluetooth transmissions, and all of them are in this power band. Below 120, there isn't anything that's transmitting. So we don't really have low power devices, and we don't have a good amount of technology at hand to have our existing devices work at low power. Whereas LoRa, as I have mentioned, will work in minus 120 dBm and below range, which means it's going to take only picowatts of power. And if you go back to this slide, if we are going to work between minus 125 to minus 140 dBm, we are talking of 10 kbps kind of bandwidth. And I'll tell you, this bandwidth is sufficient for most of the IoT devices that are being used in the market. So LoRa gives an advantage of really communicating using low power. So what are the advantages of LoRa? LoRa uses a spread spectrum based modulation technique, which means instead of a narrow band platform, which requires a very high power spectral density, and it requires high quality filters to design and communicate with devices. Actually, designing high quality filters is not so much of a challenge. The challenge is they will consume more power because they'll be focused on very narrow band kind of transmission. Whereas if you use a spread spectrum, you spread the signal over multiple frequencies, you will consume less power. So LoRa demodulates -20 below the channel noise or interferer. As we have seen, our channel noise in SAKEC was in the range of -60 to -120, and LoRa is giving us far better sensitivity. It's giving a better signal to noise ratio. So even if there's a lot of noise at say -60 to -120 dB, this noise is typically narrowband chatter noise, and we are using a spread spectrum kind of a thing. So we'll be able to catch the signal in this noise also. Another advantage of LoRa is it is basically orthogonal spread spectrum technology, which means it can work with sub-zero signal to noise ratio. It is orthogonal with other non-LoRa communications, and it is able to survive even if there were other FSK technologies that are there. The advantages of LoRa, the way it has been designed, I mean the chips, LoRa, all you have to do is basically buy a LoRa chip and put it in your device. Like you buy a Wi-Fi chip or a GSM chip. When you create your own hardware, along with the microcontroller, you generally put chips for various kind of communication. Either you have a serial chip which allows you to communicate over USB, or you put a Wi-Fi chip which allows you to communicate using Wi-Fi, or you put a GSM chip which allows you to connect using our cell phone. So all you have to do is, instead of that, you put a LoRa chip, and LoRa chip actually does have a very fast lock time to an incoming signal. So as soon as you make your device operational, it will be able to latch on to the network and start working. It can exploit very high efficiency switching power amplifiers. When you have a switching power amplifier, what you're doing is you're keeping it off for some time and then putting it on for some time. That way you're conserving power. So you're not keeping it power on all the time. And because we are using spread spectrum, we don't require very accurate frequency references. So the devices, the filters that we use, you don't have to worry about tuning them or have a high quality manufacturing capability to design these filters. We'll be okay with some sort of a issue. I mean, typically when you make your own RF devices, what you will see is if you're not doing a good soldered quality, that itself will start taking some kind of power, or it will have some kind of interference being generated. Now all of this you'll have to, when you make devices based on GSM, very focused devices, or Zigbee, these issues become a design issue which you have to take care of, and then you have to have very good manufacturing facilities to make your PCBs or get your devices soldered over there. Here you can live with some inaccurate frequencies. So I'll just go to the architecture a bit about LoRa. It is a fully bidirectional system, which means it can transmit data as well as receive data. It is a standard protocol. So a LoRa chip will work anywhere in the world. LoRa networks today are deployed in over 168 countries. So it's not something which is, say, US centric or Europe centric, where we have not seen these networks. Even in India, we have seen there are people who have rolled out LoRa networks. And Tata Communications is one that I know. I've used their network for some time. So their network last time when I knew was available in more than 50 cities. So it's a standard protocol, it's a standard network. I'll tell you some more advantages of LoRa as we go ahead. It is secured end to end. So it does not mean that you are using a low power and just small data rate kind of technology, which means anyone can jam your network or anyone can come in and steal your data. That's not there. As I had mentioned, it is easy commissioning. The device is able to find in the available LoRaWan service provider gateway and then start communicating with it. It has got built-in mobility, which means it can hop over multiple networks, or a device that you manufacture here in India and you take it abroad. Since the LoRaWan standard is the same and your LoRaWan device need not be tied to a particular network. All you got to do is get it activated over a new network. There is roaming capability built in, so you don't have to configure your devices at the device end like when you do with your cell phone. I mean, you must have remembered the earlier types of cell phone. When you went to a new city, you had to manually configure and select an own network. Now with cellular technologies and roaming being allowed, they are able to latch on to a service provider which has got a agreement with your base service provider. So with LoRa, it is a built-in capability and it gives you network scalability. LoRa, because it uses low data rate, you are able to connect a large number of devices to a gateway, which means if you build a gateway of a slightly higher strength or higher capacity, you automatically are able to scale the gateway. Whereas in cellular technologies, your end devices take a huge amount of bandwidth. So typically, the problem in my home is there are only two people who use internet in my building. Internet using wireless broadband. And it's a bit surprising, but there aren't many people using net in my house. Others are satisfied with what their mobile coverage gives. So there's no service provider in my house who's laying a cable. I don't have MTNL network in my building. I don't have Geo network in my building. So we are using network from Tikona, which is a wireless network. So what they have done is they have put a tower, a small antenna on the top of my terrace, and that antenna is talking to the tower. And Tikona is a Airtel service. So there's no cable that has been laid to my house. Now we get connectivity which is fluctuating because the tower, it has to service so many connections within the area, and based on the demand, it kind of drops our bandwidth rate at times. So those kind of things are not a challenge in LoRaWan. You can scale the network very high because the devices use very low bandwidth. And here is a typical architecture. You have these end devices. So some of the applications that I have shown are tracking pets. So pets or animals in a farm. In the US, you have large farms and you have your animals grazing in that farm and they run into acres. So there used to be a challenge on how to make sure that the animals are within a particular perimeter and they have not trespassed into other area. they all have huge number of animals with them. So typical farming in the US is large in quantity, and any technology that you use other than LoRa had their own challenges. If you ask them to wear those Fitbit kind of bands that we are wearing, so armbands devices in on the animals, and you had to have sensor receptors which are very close. So you had to lay a kind of antenna network within the farm. So all those things are gone now. So you have animal tracking devices, or you have smoke alarm devices. If there's a fire in some part of a forest or some part of the field, you are able to know it earlier. As you saw that device which I had shown in one of the earlier diagrams, the device is very small. It works on a battery and you can drop it anywhere. And with triangulation, you can know the location. So even if the device is picked by someone and moved somewhere else, it will still be available and you will be able to track where it is. So making these kind of solutions, fire detection devices is becoming cheaper. Water meters or trash container. I'll talk about it in a bit. So these are all your end devices, vending machine monitoring devices. They are connected to a concentrator or a gateway. So LoRa communication is device to a gateway, and the gateway connects to a network server, and network server connects to an application. Now there are certain advantages is what I have shown, the concentrator or gateway is being connected via Ethernet on the backhaul. So when you imagine this network of this kind, the gateways also have to communicate with other gateways which are connected to your network server. So if you look at Airtel gateways, the towers are either communicating to other Airtel towers, and then they are sharing the bandwidth, which is a very inefficient way of laying the network. Or what you do is you lay a cable from your gateway to a central location. So typical networks that you will find is a small collection of gateways. They will talk to one bigger gateway. That gateway will be connected via a cable, and that will be sending data back. So LoRa gateways typically allow you to do the backhaul on Ethernet, which means you can have a LoRa gateway put in your house, and you can use your home Wi-Fi, put in a network adapter onto or a network cable onto your gateway, and it will start transmitting the data back to your server, and then you can have various application servers connecting over there. So like a telecom service provider, you could become a LoRa service provider. People can have their own applications in their office premises. They connect to your network using standard technologies, and these gateways connect to the network server either via 3G or Ethernet. So some of the implementations that we have helped people roll out in India, what we have done is we have given them gateways. So I was involved in developing software for gateways as well as some end device applications. So the gateways, we have bought standard gateways with standard antenna and put in connectivity software over there. And these gateways have 2 GSM slots in them. So we have put 2 chips. So anyone who's a LoRa solutions provider, they use these gateways. They put in a local telecom service provider's chip, Vodafone, Idea, Airtel, Jio, whatever you want, and then send the data to backhaul. And use your LoRa devices at the front end, which connect to this gateway. So this is a typical architecture, and your network server can stay in the cloud now. So you don't really need a good physical location as a network operating center. If you look at telecom service providers, they have big buildings which work as NOCs, as they call it, network operating centers, from where they are managing all their gateways, communication, bandwidth, and all of this. Here you are using the existing infrastructure that's available, already laid out. You're not laying a new infrastructure. So you can basically have your network server on Amazon Cloud, because each of this, if you look at, except the gateway and the device, every rest all is software, and the software can be hosted anywhere. There are other considerations of the architecture that you have to take is IoT cannot support connection-based systems from an energy standpoint. So if you look at meter is simply sending a data, or a pollution monitoring device, it's simply sending the value of air quality or sound at that point of time. So you don't require too much of two-way communication or configuration. So this LoRa network allows you a non-connection based network. Also, if you were looking at scheduling means you're trying to control devices from a remote location. Then scheduling will require you to be connected all the time. So you cannot have connected devices, or if you have connected devices, then you will need to have a handshake on a regular basis. I am alive, you are alive, I am alive, you are alive. Now I have a message for you, or I have a message for you, that kind of a thing. Thirdly is LoRa takes the advantage of a license-free band. One of the main reasons why LoRa is also very, very cost effective is you're not using a licensed band. 3G, 4G, 5G, GSM networks use a licensed band, so they pay a huge amount of telecom fees to the government. Whereas LoRa is license-free band. That means either you can use 433, 866, or 2.4 gigahertz. I mean, we don't see LoRa implementation on 2.4 gigahertz because we don't get a good range. We see them typically on 433 or 866 megahertz, which allows you to. So this is basically the range that's used by our radio signals. It's RF. This is RF range, and RF has got a capability to reach long areas. It's also got a capability. So what we have seen is our LoRa devices are working very well in the basement. So if you want to develop a parking solution for a mall, which is like 2 or 3 levels below the ground, these signals reach there. So this is typically the architecture of LoRa. And here what I have seen is shown is the implementation. You have LoRa devices, you have different kinds of LoRa gateways, and then your user interface and your applications. So if you have a metering application, you can build your own billing application as to who's using what and all those kind of things, and just connect to a network, LoRa network server, which is taking data from your LoRa devices. So there are 3 classes of operation of devices, which is very, very essential to understand about LoRa. Class A are basically, as I said, battery powered sensors, and they are not using two-way communication. So they are simply transmitting their data onto the network, and very little communication from the tower in terms of activation, that kind of a signal. It's virtually connectionless and no downlink. It's not taking any commands from your gateway or a tower. So this allows you to have very low power, and this can be used for applications where you don't need too much of control. Class B devices are beacon kind of devices. So there's a handshake going on. There is some amount of latency between handshakes, so you cannot do real-time control or near real-time control, but you can do decent amount of control with this devices. It's based on slotted communication, synchronized. So suppose you have a communication happening every, say, 1 minute. So you will know that you'll have to listen to the tower every 1 minute. It's slotted communication. Many of these things are now becoming more and more configurable as LoRa is improving, thus giving you an advantage of energy and data saving. And Class C devices are continuous devices, so they typically use mains power. They are not on battery. They are used for things like gateway. So here are typical end device examples. So here's a garbage bin, which is an application which is becoming very, very popular in municipalities. So garbage bins communicate the state of the garbage, say once every 2 hours or something. It says that when the device is full, when the bin is full, only then they will send a truck to clean the bin. This way, municipalities are able to save on manpower and vehicle, as well as they don't really have to kind of send a truck every time to pick up a bin which is not full. So this is an implementation. There are other implementations of temperature monitoring sensors or sound pollution monitoring sensors, which are simply transmitting the data, and the application that is receiving it, it has to act on that data and decide what needs to be done. So these bins are becoming very popular nowadays in India, and many municipalities have floated tenders or implemented these solutions. Class B devices, as I said, was the kind of sensors that are reporting moisture. So imagine this is a sprinkler, and on this sprinkler you have mounted a moisture sensor. If this were a LoRa sensor, it would keep on sending the data, the moisture, ambient moisture data around the sensor. And if it is raining outside, then you don't have to switch on the sprinkler at all. Or if there is reasonable amount of humidity, the plants will be okay to live with that humidity. But if it becomes very hot and dry, then you have to switch on the sprinkler. So this is a Class B device which is listening to a command from the central location or the application that is driving it, and it will help you switch on the sprinkler whenever needed. And here there's a Class C kind of implementation. Here we have street lights. So this smart street lighting is again becoming very popular in India, and there are many towns now which have rolled this out. So if your car is going below the lamp, it will light the lamp, or you're walking below the lamp, it will light the lamp. So these lamps have PIR sensors installed in them, and they are LED lamps. Each of these lamps are now individually controlled. So if there is no movement below the lamp, they will dim the light so that it's reasonable enough to show that there is lighting on the street, and it's not completely dark, so you're comfortable to walk over there. And as soon as you start approaching the lamp will light up. And if you're just walking across the street, so we have implemented this solution in IIT in one of the lanes. So whenever you walk towards the lamp, it will light up. Or when you take a car, you will see that the third lamp in front of you is also lit, because the car moves much faster. So based on the PIR activity and the data sent by the PIR, we are actually switching on the number of lamps that are required. So for this, you require real-time communication, and that's the Class C communication. So that's another great advantage of LoRa. It's not one single communication which is always on, which is there with Wi-Fi, Bluetooth networks. Here, you're really saving on bandwidth. So these are some of the solutions that are built. And so here, the top left slide shows a sound pollution monitoring network in Geneva, where our team has worked with the providers of these people. So they are, as I said, they have a standalone device. You can actually put it in various buildings at various locations. You can simply tape it over there so that the device doesn't fall off, but you don't have to worry about charging power. Then these are street light solutions. Here's a device by 11x. So this 11x networks gives you a standard device for interfacing, and then you can put your sensors, your temperature sensors or pressure sensors or any other sensor, and attach it to this device. That way you suddenly make your system LoRa aware. Here's a cycle theft application which is used in Netherlands. So each of these cycles, they have soldered a LoRa device over there. So if you say that someone has kind of stolen your cycle, this cycle is transmitting its location. So the police enable tracking of that particular device. Otherwise, because of privacy considerations, these devices are, these devices are transmitting, but that data is not recorded. Then police request the LoRa network providers to switch on the tracking for this particular device number, and then they are able to locate where the cycle is and such. So these are various solutions that are built. Our team has been involved in building these solutions for water metering and other things also. So one of the great advantage of this is, as I had mentioned, you don't require huge amount of real estate, or you don't require towers which are kind of mounted where you have a straight line of vision kind of connectivity. This is RF. So you can have the gateway inside of your building also, and the device will talk to it. So typical implementations we have seen with say one municipality in China. The municipality is not using any telecom service provider now. They have their own metering solution. They have set up their own network. As I had mentioned, this is a license-free band, so you can put your own gateway. So municipality has many offices, either they have leased or they are their own within the city, and so they have spread a network of LoRa gateways within their office. You don't have to go up a tower and mount them, and probably one odd gateway, if you are using gateway to gateway communication, may be mounted on a tower, and then they are running their own applications. So they are not dependent on any service provider. They are not incurring any cellular cell phone kind of costs. They are simply mounting their devices within their offices, and they are using a LAN cable to connect the device to the office network, and they are pulling the data. So suppose you have say water meters that are sending 1 kilobyte of data per day, or 10 kilobyte of data per day. So 1 kilobyte of data, if you look at, and 1,000 such devices, you are just sending 1 MB of data. So if you are looking at, say, 5 lakh or 10 lakh water meters within a city, and trying to get data from that even then you're not going to use even a GB of data, which is much less than the data that you use on your cell phone or a WhatsApp. So if you make a gateway and you put in your SIM card into that gateway, and that gateway is now connected to, say, thousands of devices, you are basically incurring a telecom cost of, like, typically nowadays I'm paying 500 rupees for 3 months of bandwidth, where I get 1 GB, more than 1 GB per day. So in 500 rupees, I'm getting that bandwidth, which I'm able to connect more than 100,000 gateways. So that's the kind of advantage LoRaWan is now bringing in. You can roll your own network. You don't have to go and apply for licenses. You're not worried about interfering with other devices. You're working on RF band, which is license free. The other advantage that LoRa brings, and I'll quickly talk to you about, is adaptive data rate. So the way LoRa is structured, you have got multiple channels, and you are using a channel with a specific data rate. The advantage of this is, if you are able to have a faster data rate, you will transmit faster. Your device will be on for a less amount of time, and it will consume less battery. As I've mentioned earlier, many of the devices that we are making, we are keeping the power on for a less period of time. So if you know the signal strength of your channel, you can basically select a channel which is, say, having a high data rate, and quickly transmit your data and shut your device off. Or if you are like very far and you're not getting good connectivity, even then you can lower your data rate and transmit. So basically, as I have shown over here, if you are 14 kilometers away, you might still be able to get a good data rate and transmit. But if you're not getting a good data rate, you can still transmit on, say, 244 bits per second. That's 1/4 of a kbp data rate, and still be able to send your data out. And the data being less in quantity, you can be sure that it will reach the destination. So this is very advantageous for the network as well as for the end device. As I mentioned, an end device with a good radio channel will use a higher data rate and transmit. If the data rate is not so good, it will still be able to make sure that the data is gone by lowering the data rate. It is also good for the network. Basically, in a network, if say suppose one tower is loaded with devices. So right now, globally, the implementations that we are seeing, we are not seeing too much of gateway load because the technology is still new. But slowly, time will come when these gateways will start getting full. And we typically have implemented nano gateways, micro gateways. So nano gateways are very small gateways with less area of coverage because they are using less power. So these kind of gateways, if they get full, we can basically switch the device. So a LoRa device typically will talk to all the gateways within the area. Then the gateways will negotiate amongst themselves and will say that, okay, you don't forward the packets from this device to the network operation. I am managing that. And if any point of time, if that thing fails, then the other gateway takes over and starts transmitting the packet of the device. So a device to gateway communication is always happening, but the backhaul can be reduced. So this way, you're basically able to configure the network also. If there's a large amount of load on a particular gateway, then you reduce the signal strength or switch the devices to other gateway. The devices may send on low data rate, or they may incur slightly higher power, but at least the network will not go down. There will be no congestion. This is what I have actually shown in this diagram. So you could have lower time on air, larger gateway capacity, longer battery life, those things. So I'll quickly now go through an implementation. Europe, India, it's 863 to 870 megahertz. These can be really used by network operators, and you can create your own network. So one of the set of people I know in DBIT, Don Bosco, they have created their own LoRa network within their premise, and they are tracking, they're monitoring temperature. So if you have some air-conditioned classrooms, you want to be sure that when there is no one inside over there, the ACs are switched off, or people are not using ACs as you know, I mean, when you start using AC below 24 degrees centigrade, or if you are kind of using it at 20, 21 or 18, where, and many people are used to doing that, then it consumes far more power than if you operate the AC at say 23 or 24 degrees. So now you have temperature monitoring devices put in the room, and they are battery powered, and they are communicating on LoRa. And there's one gateway they have put within their premise, and now they are able to track typically what's the temperature scenario within their office. In India, you typically have 8 channels with from 240 bps to 5.5 kbps. So that gives you a good segregation, and you can have actually 24 such slotted channels. So you get a decent amount of bandwidth. One thing about security, as I had mentioned, so one of the questions that will come up is if the devices, if any gateway can read it, if today my gateway can read it, and then you put up your gateway can read the device. So what is the security? I mean, if I'm sending some sensitive data, can't it be tracked? So the way LoRa is designed, so LoRa has got 2 network authentication keys. One is with your network server, and one is with your application server. So suppose I want to monitor my temperature and I'm using say Tata's network in my office. So when I put a device on the Tata network will know that okay, it has to take the data from this device and transfer it on the backhaul to my application. So that's one set of key, that's the network session key. So I set up a network with Tata, and these devices transmit on that network. But if Tata were to look at my data packets, and if they wanted to encrypt the data inside it, they will require my application sessions key, which I am anyway not sharing it with the service providers. So only when these come into my system, then the data is decrypted. So LoRa by definition, by design, has these 2 keys implemented. So anyone who is implementing a LoRa network, or people who are coming up with LoRa devices, will have this security protocol generated. So with LoRa, when a chip is manufactured, each chip has a 32-bit identifier. So each device has a unique address, and then you have a network session key and then activation session key. These 2 keys are created when the device is brought on the network. So that way, your device can be used by any of the networks, and you can still have data privacy. I'll not go too much deep into that. And typically, end device is configured at production time. Many of the networks are giving LoRa devices. So as I had shown you that 11x box. So what you do is you simply take that box, and on top of that you put in your sensors, you put in whatever you want to do, and start using it. That box is pre-activated. You don't have to do anything, or else you can create your own device, and you go to the network service provider and say that, okay, I want this device to be activated on your network, and everything can be done on over the air. The keys can be assigned over the air, and it's reasonably easy to deploy this, or you can create your own network. As I've shown in this photograph, we have the blue device on the right is a nano gateway used to implement within a small campus, or something that looks like a Wi-Fi router is a micro gateway, and this is a macro gateway uh, that has got a very high capacity. So these kind of gateways you can set it up anywhere, and then you can connect these gateways over existing TCP/IP backend. Your packets will still be encrypted, so no one will be able to. As you know, TCP/IP you can do sniffing. So TCP/IP will know there's a packet going on, but it's a LoRa packet. It's not a standard TCP/IP packet. The data inside is encrypted, and that way you still have security and you have your applications that are built in. Typical network server architecture, which I have explained. These are the gateways. There's an operations and maintenance center. There is a persistent temporary storage. Since these devices are not sending huge amount of data, you can actually log in the data for a large period of time. Or if for some reason these gateways are not able to communicate back to your application, still your data will remain within the storage, which is unlike any of the other telecom service provision. They don't have the capacity to store this much amount of data. So your data can be available later also. And then at the data access subsystem level, you can have things like access control, who all can talk to your device, and you can have certain services, basically configuring your gateways, and then at the leftmost you have your cloud application servers. Here you do temperature monitoring, and you know which ACs are working at a lower temperature, or you do your billing application and then generate energy usage bills at the end of the month. All of this can be done. So this I have covered the fundamentals of LoRa, some of the applications, and I also tried to put in what is it in for electronics engineers, or we as teachers or industry people, what can we do? So we can build new devices and applications. We can do development of sensor networks, or we can even build in adapters or modules. So some of the applications, I mean, college projects that I saw last year, where people have built in an adapter that will work with your electricity meter, and so it's connected between your power in and the electricity meter, and it's LoRa, so it is transmitting the meter reading. Or they have made their own meters, very smart meters that work on LoRa. We can also build training kits for people to have a appreciation of this technology and learn how to use it. And a whole lot of applications can be built. You can put in lots of intelligence. So basically, wherever you see that you don't require large amount of data. So if you look at this Fitbit kind of devices, these devices communicate with your cell phone on Bluetooth, and then use the cell phone's backend power to communicate to maybe a central server where they are running your applications, or you have your application based in the mobile phone, and then you're trying to track your health monitoring parameters all throughout the day. Now this, if you were to switch to a LoRa kind of device, it will still work on a watch battery on which this Fitbit kind of devices work. You can use microprocessors which are very, very small. You can put in your LoRa chip into that. So basically have a LoRa device as an armband wrist, and then it will communicate to a tower which is away at very low power. You can have these kind of health monitoring devices, mobility monitoring devices. They are giving it to uh, aged people and whose children are abroad. They just want to know that their parents are mobile during the day, and if there is no activity, then they get an alarm. So they have configured their phones in such a way that they know that these are the sleeping times of their parents. So at that time, if there's no activity, they are not disturbed. But if it stretches for some time, then they're able to track the alarm and then they call back to India to their home. So many applications are now coming up. They can build it. And for computer engineers, I mean, you can build in solutions. So you can do prioritization of packets. So once a huge amount of devices start coming in, as we know that these devices are not being, if they are like class A devices, their packets could get delayed if there's a congestion in the network. So you can actually at the gateway end build a software to prioritize the packets, or you can build intelligence applications as to what kind of communication is happening between these devices, when are they communicating, or how quickly are your dustbins getting full, or what kind of a route is required to pick up the dustbins, because earlier what these trucks used to go on a fixed route. Now there may be a dustbin which is full in one area and another dustbin which is full in another area. Do you send one truck or do you send two different trucks? So those kind of intelligence applications, plus at the back end you can build newer databases that are coming in. So all of this can be built in. So, thank you. This is what I wanted to cover. So I thought of giving you an appreciation of why this technology was envisaged, how it has been envisaged, how it has been built, and where all it is applied. I'm open to Q&A.
Thank you so much, sir, for this informative session. I'm sure participant has get lot of knowledge about LoRaWan. Now there are few questions. I will read it for you, sir.
Yeah.
The first question is, what is the LoRaWan frequency band in India?
So as I mentioned, it is 863 to 870
Okay. There is a one more question.
megahertz. Yeah.
Oh, there is a one more question. The question is, what is the standard LoRaWan protocol?
See, LoRaWan protocol, if you go to www.loraalliance.org, you can download the protocol. I mean, it's like TCP/IP and others. LoRa is a protocol in itself, and you can download. It's a easy protocol to implement. I've seen college students implementing it very easily. So what they have done is they have bought simple LoRa chips from the market, and then they have created their own gateways and own devices. See, either you can get in the market, you can get something like a ready-made adapter, which has the protocol built in, and then you interface your sensors to that, or else you create your own device. This can be the protocol can be downloaded from LoRaalliance.org site.
Okay. Sir, there is a one more question. How long can a beacon last for?
Well, beacon typically you can configure. So you don't, on a LoRa network, what you do is you don't keep your listening window for large. As you know, LoRa network, I mean, any gateway can pick it up. So if you want your device, you want to make sure that your device is kind of readable. I mean, it's whatever data it has transmitted, it is coming to your network. You put in multiple amounts of gateways. So putting multiple gateways is much cheaper than keeping your. See, when you say, I mean, what I understand from the beacon is you have your listening window, which is open. So say you open your RF receiver for say 1 second and you receive that, and then you switch off your RF receiver and then you open after 1 minute. And again, listen for handshake signals. So either it will be a question of interval between two slots, or it will be how long is a slot open. So typically you don't keep your slot open for too long, but you keep on multiple gateways. That way you reduce the cost. But these are configurable, and since the LoRaWan protocol is kind of evolving, with more and more implementations coming in, they are now adjusting these kind of slots in their newer protocol releases.
Yeah, thank you so much, sir. Thank you so much, sir, for taking time out from your busy schedule. Now, just please accept a small memento as a token of appreciation from all of us. Thank you so much, sir. Thank you, sir, on the behalf of
Okay,
Shine.
thanks, sir.
Yeah, thank you so much, sir.
Yeah, thank you. I'll log off now.
Yeah,
Okay, thank you.
thank you so much, sir. Yeah.